When you have IVops running on your computer and you click on it, this particular screen comes up. And the screen has a hidden section on this end under modules. So you can go into the modules and, or we call it parent asset elements, and you can look all of this up. Now, what will be easier for you is if you have downloaded the 4 user manuals. There are actually, the user manual is broken up right now into 4 parts. So you can download each one of these. And one of the things I added to the user manual part 1B is this section 2.7, which is a checklist to verify that you have set up your plan correctly. Now, when you use this checklist, and I will go through it a little bit in the middle of the class, you will find that it is, you can start with a simple plan, you can go to a more complex plan. But the main purpose is to avoid making some errors or skipping some steps and then getting into a difficult situation later on. So the first step, and if you look up chapter 3 of the user manual, you'll see that there is the simple influent. We will not discuss the complex influent in this class, but in a more advanced class, we can talk about it. Now, within the simple influent, you just have 2 child assets. One is the flow controller, and one is the lab. So the flow controller tells you what the flow rate is, and the lab will, in the lab, you will enter all the values for the characteristics of the influent that you need. Now, when you go to the top menu here, you will see certain items like equipment, which is something we may touch on tomorrow. We'll try to do a bit of calculators. There's an MCRT and HRT calculator here. We will not cover what is under operator right now or under asset manager. But one of the things you will need is units. So you have to select whether you want SI units or US English units. And you can switch at any time. For example, right now the flow rate is 5,000 meter cube per day, but if you want, you can switch it to US units and it will give you the flow rate of 1.32 mg. So you select the units over here. We will not cover the scenario analyzer, which is used for troubleshooting and for predicting conditions in the future. But it is something, if you're doing a design or if you're trying to verify some other model that you have set up, one of the things you get here is not only you run an independent model, but you can also run scenarios over here with different conditions. We will use these features to position items over here in our workspace. And then when we start running the model, we will go over this section, which is the engine. Today, we may touch upon a little bit on how to attach data that is in an Excel file and import it. And that Excel file data may also come from SCADA. And I will show you a little bit of the results and the reports. Right now, you should look up the user manual. It is there in chapter 2. The report section, you can export data to an Excel file. We can cover it if you have some time tomorrow. We can do a little bit of the reports. So let's go to the influent. So in the influent, let's set up a plant for 10,000 meter cube per day, which is about 2.5 MGD plant. So if you want, you go into the attributes here, go to the flow controller, change the flow rate to 10,000. We are not running a dynamic simulation right now, but if you do run a dynamic simulation, you can bring in your time series data over here. So what I will do is tomorrow, I will try to cover a little bit of the time series data and bring that into the computation so that you can run 24 hours of data, or you can run 1 week of data, or even 1 month or 1 year. So now let's go to the second child asset under influence, which is the lab. Now in the lab, there is a summary section at the top, which is essentially summarizing the main constituents. So what I will do is I will try to cover the main constituents, but I'll make only a few changes. Let's say you have data on your TSS, and that is 250. You have data on your VSS, and that is 240. It automatically computes the inner TSS by subtracting one from the other. Let's say the fraction fermentable, we will change this default, is 80%. That means 80% of your influent can be fermented if you have a ferment. Let's say your COD. Now, here you need to be a little careful, and you need to look up chapter 3, which discusses this in detail. You should not be entering a soluble COD which is greater than the COD, because if you do, it'll give you a warning that your soluble COD cannot be greater than the COD. But let's say our influent COD is 500. And let's say the soluble COD is 240. So it automatically computes the particulate COD over here, which is 260. These are the soluble non-biodegradable components which come up through calibration and looking at your treatment system if you have an actual treatment plant. We don't have any data for now, just leave it around 10 or 15 unless your wastewater is much stronger or an industrial waste where it can be higher. Now, the BOD is actually computed internally, and I need to take you to the section which will compute this BOD based on a coefficient we put in. But let's finish the rest of the influent and we will come back to the BOD part. Now, what has happened to a few users is they know that their ammonia for this plant is 30. Now, the TKN over here, sitting over here, is 21. Now, if you try to enter an ammonia of 30 while the TKN is still 21, it'll give you this. So let's put it back to 15 and first make the TKN, let's say the TKN is 45. Let's change the TKN and get to the SKN, which is 33. You may first set all this up in Excel and make sure you've got your influent right and all the characteristics right. If you have some nitrate, small amount of nitrate, you can enter it here. The non-biodegradable components are here. Then you go in here to phosphorus, same thing. First, I would suggest you get your total phosphorus right. Let's say that is 6 milligrams per liter. Then your total soluble phosphorus, let's say that is 3.5. And let's assume the OP right now is 3.0. Now, if I accidentally enter a value which is greater than the TSP, it will again give me this warning, so I have to go reset it. Let's say the alkalinity of this wastewater is around 250. You may have pH data, you may not. Then you have other sections over here. You can leave it alone at this level of complexity. Later on, you can enter values, but in most cases, your influent iron and aluminum will all be 0. And then you would, if you're adding iron or aluminum, you would add a chemical feeder, and there you would add the iron or aluminum. Let's say the DO, there's hardly any DO in this influent, 0.1 or 0. Now, you're allowed to define certain microorganisms that are there in the influent. You may have a small amount of microorganisms, but for now, we'll leave it at 0. The max amount of microorganisms, unless you're taking in sludge from another plant and feeding in through the influent, it'll be probably 4 or 5 milligrams per liter for OHO, and probably 1 or 2 milligrams per liter for AOP and NOP. So that completes the influent, except that we have, let's say our BOD is not as high as 330. Now this gets into a little bit of a tricky situation, and I've explained that in the user manual. What you need to do is there is a place where the coefficient is entered, And if you do need to change it, it's not that important, but if you do need to change it, you will have to go into models, you'll have to go into parameters, SGM, which is the suspended growth model. You have to go into conversion factors under that. And under conversion factors, you'll see the biodegradable COD. This is the biodegradable portion of your influence COD. So you take the COD, subtract out the non-biodegradable particulate and the non-biodegradable soluble. So the remaining COD is biodegradable. That to the BOD ratio here is 1.75. Let's say it truly is at 1.8. And you change that. And then if once you have changed it, when you run the model, it will, or when you get out of that icon and go somewhere else and come back, it'll give you a different BOD. So now the BOD is 260. Really, this value, if it is closer to 250, you have to play around with that ratio. But again, the BOD is not that important for us, so let's not get too worried about it right now. What is more important is from your BOD data, you get to a COD data, you enter your COD data, and then you can go back and change that COD to BOD ratio. We will make some changes in the model down along the road to make it easier, but that'll be like a few months down the road. You'll have another part of this menu where you can check all this right on this screen. So now we have entered the influent, and let's say downstream of the influent, we have a screen. So now you have your screen for your plant. This is your headwork screen. You can go in and press on this and press on this and connect these two, and you'll have a flow line connecting the two. Now, I will run a very simple plant initially. Let's say the plant has just a screen and nothing else. So if you want to complete the plant, you can put an effluent and connect this, and that's your plant. Your influent, a screen, and your effluent. If you want, you can run this, and it has run. So you press the run button, it has gone through the run. Now once you run it, you can click on a flow line, and it will give you the characteristics of the flow line. Now, one of the things you will see is that ammonia, TK, and all are the same as the influent over here. But one thing that is not matching is your TSS and VSS. Now, I've discussed it with the development team that is working on this, and we could force it to come out the same. But one of the flexibilities allowed in IViewOps is that you could have different types of influent, and each can have different COD to VSS ratio. So, if you want this value to be the same as what you have in your raw influent, which is 250 and 240, you will have a tool in a later release which will allow you to do it right from the screen. But if you're very worried about it, you could go back to SGM and convert this TSS to COD ratio for excess to something like, let's try 1.0. It will, later on, it will tell you what that value should be so that you don't have to guess at it. And now if I click on this, this is coming at 266 and 256. So the influent is actually 250 and 240. Since I increased the ratio, it went up from around 205 to 266. We can change it a little bit once more and get to the correct value. Again, this is not going to affect your calculation, but since some people get concerned about it, I'm showing this part. You will have a tool which allows you to figure out this ratio right on the influence screen later. And then you will have to go, so now it's 254 to 244, so it's pretty close to what you specified in your influent, which was, if I look at the lab, it was 250 to 240. So now you've set up your influent. Let's go to the screen. If you look at the screen, it's very simple. There's only one parameter that we allow you to play around with, which is the amount of particulates that are removed in the screen. That means particulate COD, particulate GKF. And except for fine screens where the number may be closer to 1%, this number is usually very small, and it's only the particulate matter that is being removed. And here, just leave it at the default of 0.25%. Now, if you click on this line, this is the effluent coming out of the screen. There is some, you will see that there was 254 coming in, PSS, and what is going out is 253. There's a little bit of particulate removal. But this is a very simple plant. It just has a screen. But your plant, you want to now put in the rest of your treatment system. So to do that, it's very simple. You want to delete this line, and you want to insert others. So go to this delete, okay, under the modules, not under scenarios. This is to add scenarios. Go to this delete and click delete, and it will delete the flow stream. Just move this aside. Let's go back to headworks in the modules. You have pump station, you have grit chamber. Let's say we want a grit chamber, you just lower the grit chamber and put it in here. Same thing, the grit chamber at the top level is very simple. You just say how much of particulates are removed in the grit chamber. Let's say that is more like 1% of your particulates for some reason are setting out in the grit chamber. Now the grit chamber does ask you one other thing. It says you have a grit tank. And this is where you start getting into how you set up tanks in IViewOps. Okay. Seems there is a bit of an internet problem. So you have a grit tank. Let's say the tank is 6 feet deep or 2 meters deep. Okay. So it's 2 meters deep. If I want to switch units and look at US units, okay, that's 6.56. But for now, I'll stay with SI units. It's 2 meters. Now, let's say you have two parallel rectangular grit tanks. You can have circular, you can have rectangular. So I want rectangular, two parallel grit channels which are rectangular. I go into this cells, these are the grit cells, and I go into this add, and I click on this, and it gives me one rectangular cell. If I want to add a second cell, I go here, click on the green plus sign, click on rectangular cell, and it gives me a rectangular cell too. So now I have two parallel grid cells. Okay. Now, let's say I want to name these so that every tank is not called tank. So let's say I want to call this grid tank system. Okay. Grid tank system. So I go into the name and I rename it here, and it gets renamed in the asset hierarchy. And within that, let's say this is grid tank 1. Okay. And the other rectangular cell, I'm going to rename it grid tank 2. So now we have the two tanks which are named. Now it gives you a default length and width for each tank. Obviously, your grid tank is not this size, at least for a 10,000 meter cube per day plant. Let's say the grid tank is 3 meters long, which is about 10 feet, and 1 meter wide. So this particular grid tank is 3 meters long, 1 meter wide. The other one is also 3 meters long and 1 meter wide. So now you have set up the dimensions of your two grid tanks. It gives you the area and the volume. The other part that is important is you have to define whether the tank is online or offline. And this can be connected to your SCADA system if you are using the model in your plant. So let's say the grid tank number 1 is online. And let's say number 2, I want to make it offline. So you can uncheck this and it'll become offline. If you look at the on-off controller, this value will become 0 when it is offline. Don't worry about these other things for now. Just let's just stay with, okay, you want to keep the tank online or offline, you do that. If you look over here, since we made one tank offline, it will say one out of the two is available, the other one is not. Some of these definitions will change a little bit as we get more into the asset management side later on. So you have two tanks. You have made one of them online. You have set the other one offline. Okay. So now we finished the grid tank. Now let's go back here, scroll over here, and you will see that, okay, you have the option of equalization, but at this stage, let's not go into equalization. We're just setting up steady state. You have the option of setting up a primary clarifier. Now, if you set up a primary clarifier, you do need to look up chapter 2 and all the sections of a primary clarifier and get familiar with it. If you're just a beginner, I suggest you set up the plant without a primary clarifier, and then you gradually go through the steps. You can insert it later, and then you learn how to set up a primary clarifier. What I will suggest is, as a beginner at the early stages, when you study these things of a primary clarifier, there's a section over here called model, which is, do you want to run all these models, which is the suspended growth model, etc., in a primary clarifier? Let's say no. We don't want to run a computational model for biochemical reaction in the primary clarifier. You can turn it on later once you've figured out how to set it up. So let's say no. I will go through the components, processes, and all in the second half of this class. Now we get to TSS removal. Now there are different ways you can set up the primary clarifier. And you have those options here. You can do component-wise if you have different amounts of particulate phosphorus versus particulate nitrogen that are removed. But we'll stick with overall. And let's say this clarifier is removing 60% of the TSS. Now you get into the tank features of the primary clarifier. And here we will set up two circular primary clarifiers. Let's say the primary clarifier is 3.5 meters deep. Now, the next thing you're asked under a primary clarifier are certain values over here, which we will skip at this time, but instead we will look at the two child assets. One is an underflow controller, which is the primary sludge that is pulled out from the bottom of the primary clarifier. Now, if this plant is receiving 10,000 meter cube per day, the primary sludge flow may be max, probably maybe 100 meter cube or 50 meter cube per day. So let's, it'll be like 1% of the flow entering the plant. That's a typical primary sludge flow, or even less. So let's say it's 100 meter cube per day. We have entered that. We will not go over time series here again. In a dynamic simulation, you can say, okay, your primary sludge flow is on at certain times of the day, off at certain times of the day. You can plug that in. We will go into the tank. Now, what is this tank? This is the primary clarifier tank group. Within that, you will have the individual primary clarifier tanks. By default, the primary clarifier comes up as a circular cell, but you can delete the circular and make it a rectangular primary clarifier if you want. But here we said we will put in two primary clarifiers. So let's go here to the cell section and go to add and say, okay, I got one circular cell, go to this plus sign and you add you can choose rectangular and circular. But there is a principle that you need to follow. You would group the circular cells together, and you would group, if you have rectangular and circular in a system, you would group the rectangulars together. You would add a splitter and say how much flow is going to the rectangular and how much is going to the circular, if you have a plant with both circular and rectangular primary clarifiers. But hopefully, you're not dealing with a plant which has both rectangular and circular. Now you get to the point where you have to enter the diameter of the primary clarifier. Let's say the clarifier, we just stick with this default 15 meters diameter, which is about 50 feet diameter. And that's clarifier 1, so I can rename this and call it primary clarifier 1. Now the other one is primary clarifier 2. Okay, this one, for whatever reason, is coming up with a different dimension, but I will change it to 15 meters. Okay. Now, the depth of both the primary clarifiers is set up here. Now, the question is, are we operating one or are we operating both primary clarifiers? Let's say we are not operating primary clarifier one. If that is the case, you turn this one offline. If you're operating both, keep both online. Now, if you turn one offline, it will say out of the two, one is not available, the other one is available. So, let's connect the flow lines going from here to here, and then from here to here. Now, out of the primary clarifier, there are two flow streams getting out. One is a sludge flow stream. And in tomorrow's class, we'll deal with the sludge flow streams. But to put in a sludge flow stream for now, as if we are hauling the sludge out, we will take the sludge and put it here, and we will connect this to the sludge flow stream. When you press on this, it will be red. When you press on this, it will be green. Once the two are connected, it will be fine. So now we will get into the secondary treatment system. So if you scroll down here, after headworks, there's secondary treatment. And you put in, you want to put in a bioreactor. Now, you have different choices here. You can put in a regular bioreactor. You can put in a biofilm bioreactor. A biofilm bioreactor, with, you're allowed to put in biofilm in. You also have plug flow bioreactor, which you can compartmentalize and make it into multiple bioreactors. You have sequencing batch reactor, which is in an advanced class. You have a membrane bioreactor, denied filters, etc. So let's just put in one bioreactor right now and set this up. So if you have put in a suspended growth bioreactor, not a biofilm bioreactor, it will come up with SG bioreactor. So we have that. Now, let's say I want to call it aerobic 1 system. Okay, I'll call it aerobic 1 system because within this you have aeration system, you have diffusers, you have the tanks. So all that makes the aerobic 1 system. Okay, this is because later on I might want to add more bioreactors in series, so I have to call them aerobic 1. Within that you have a child asset, which is the aerobic 1 tank group. So now under the aerobic 1 system, you will see the tank group, you will see the diffuser system. So they have been separated out. So let's say the tank is 4 meters deep. Okay. And let's say you have 2 parallel trains. You may have 3 parallel trains or 4. Now, when we create tank groups, we group the same depth of tanks with the same types of diffusers in one group. So in complex plants, you might have one side which has force bubble diffusers and another side which has fine bubble diffusers. They were built at, let's say, different times. Then you would set up 2 parallel trains. You would have another icon here, and you would have a flow splitter, one side going here, one side going here. But you may have 3 trains on the old side and 4 trains on the new side. Let's say the old side had 3 trains. How would you set up the 3 trains of the old side? What we would do is we would set up the 3 rectangular cells in aerobic 1 right within one thing. You don't have to have, if you have 7 parallel trains, you don't have to put in 7 icons on this thing, because then it would become crazy. It would be filled with icons. So what you do here is you go in here, go to the rectangular cell. Now, you know that we are going to set up 3 cells here for the 3 trains. So we'll have to get all those right. The dimensions, the default dimensions came up. Obviously, these are not the actual dimensions, so we'll change that. Now, under the aerobic 1 tank group, you want to make it 3 parallel trains. So there are 3 aerobic 1 cells. So let's go in here, and again use the rectangular cells. Add 1, add 2, and now you have 3 rectangular cells. So the depth of all of these cells is controlled by this depth. You cannot have 3 individual depths over here for the 3 cells. If you do have different depths, you're supposed to set up a different icon and send the rest of the flow to that icon. But here we are using one icon. So this rectangular cell, let's say, is aerobic 1, train 1. Okay. Aerobic 1, train 1. Let's say this is 20 meters long, 10 meters wide. And it's online. Okay. Aerobic 1, train 2 is also, I can have different lengths and widths. You're allowed to do that, and it'll split based on volume. But just to keep things simple, we'll do 20 and 10. And then I'll rename this aerobic 1, train 3. Okay. So now, if I keep all three online, here it will say there are 3 and all 3 are available and online. Okay. If you look at the total volume, 2,400 meter cube. If you look at the individual volume, it's 800 per train in aerobic 1. So 800 times 3, 2,400. Now let's say train 3 is offline. So we take this offline, and then we go here. It'll say that well, right now the total volume is still 2,400, but effective is 1,600 because that's what is available, and 2 out of the 3 are available. So the total volume is the total that is constructed in the plant. What is operating will be over here. Now, I could decide, okay, I want this plant to be more complicated. I want an anoxic tank, and I want the second aerobic tank. So if I have to do that, I go in here and I put in another bioreactor. And now I want to call this an oxygen 1 system. Now here too, I have to set up my 3 cells with the depth, etc. So I will do that. So in the anoxic 1 system, the depth here too is 4 meters. The tank group, I'll rename it okay, and then I'll add the cells. So you got your 3 cells. I can call it anoxic 1, train 1. And let's say this is 20. This is also 20 by 10. I'll call this anoxic 1, train 2. This is also 20 by 10. And I will call this anoxic 1, train 3. And let's say this one is also offline here. Now comes an interesting part. Okay, here's the diffuse aeration, and you have to make a decision. Is this dedicated anoxic, or do you have the option of having diffusers here, and you can turn the diffusers on and off? Now, if your tank is dedicated anoxic, you go in here and you say none. Okay. That means that you do not have diffusers over here, and the tank becomes anoxic. If, however, your tank is one where you have diffusers, but you're going to switch it on and off, then you keep the diffusers, but you say the diffusers are offline. Okay. So there is a swing zone versus a dedicated anoxic zone. So for this class, we will make it a dedicated anoxic zone. In a more advanced class, we will play around with the swing zone. And we also call it a dedicated anoxic. Now what has happened is, if you look at the hierarchy, the anoxic is coming out below the aerobic. So let's say I want to move it up. So what you have to do is you have to press your mouse and you just move it, drag it up, and it'll move up over there. So you have to press your mouse, the left side of your mouse, and then you drag it up so that your hierarchy comes out of it. Now let's go back to the aerobic system, and you have your diffusers. Within your diffusers, again, if you look up chapter 2, and then some of the detailed chapters in volume 2, you have two ways of setting up your aeration system. You can set it up based on airflow rate. That means you're putting in a certain meter cube per hour or CFM of air into that zone, which would be true for SBRs and things like that. Or you can put it based on a dissolved oxygen set point. We will do the simpler one. We will do a dissolved oxygen set point. Now it asks you for alpha and beta. If you do not have any values for your alpha and beta for the first aerobic zone, enter 0.5 for your alpha. Now, keep your beta as shown here, keep your theta, which is how the oxygen transfer efficiency changes with temperature, or liquid temperature. You keep that also the same. The height of diffuser is above the floor of the tank. You could leave it at the default at 0.25 meters or about 0.7 feet. The standard efficiency. Let's say we are using membrane diffusers and they are 22% efficient at a depth of around 3.65 meters. Now, this is actually provided by a vendor when they give you a standard oxygen transfer efficiency at what depth. We will cover blower groups tomorrow. I don't think we'll have time today, but you can assign a set of blowers to a particular tank, which is covered over here. We have not set up the blowers as yet. So now we have got this, and then under the diffused aeration, you have a set point. Let's say you're operating this at 2.5 milligrams per liter. So that's your set point. Your on-off controller is whether your air is on or not, and here when it is on, that means it is on. And also, when you went into the system, you said it is online, so that's what it's on. So now, let's say we want another aerobic zone to make it more like a true plant. 1/3 is anoxic and 2/3 is aerobic. So I go in here and I put in another bioreactor. And let's say that's 4 meters. Okay, and I'll call this aerobic. Okay, within that, there is the aerobic 2 tank group. Now, if you're doing a quick and dirty design, you don't have to set up multiple tanks like the multiple tanks within a tank group. You can just specify one rectangular cell with the full volume. If you're trying to replicate a real plant and see what will happen when you take one train out or 2 trains out, etc., then you get into this. And the strength of IVops compared to others, as you will begin to appreciate, is to find out the deficiencies in the other models and replicate through operations so that the risk on a vendor, risk on a designer, risk on the utility owner is minimized. It's like when you do weather forecasting, if your meteorologist only uses one model, in most instances it will be incorrect. So they use 3 models. The same thing the field will slowly realize that every model, however popular it is, has inaccuracies. And if your question why your results are not the same as what it was designed, and by the way, out of the 50 ENR plants in Maryland, I don't think even one replicated what the design model said, which is why this was funded as a separate effort to replicate the reality of operations. So that is why all these cells and all these multiple things have been built in. But you can use a much simpler approach. You can use the approach used in other design models, and I can just say, okay, I have one rectangular cell, and this is 20 meters wide and 20 meters long and 30 meters wide. And I could get the same volume. Or I could say, okay, there are 3 parallel trains, each is 20 by 10. I will name each one of them, and I will set it up so that I can correctly replicate what is happening in the plant. So then I go in here, quickly add 2 more cells, 2 more rectangular cells, and I complete this. Again, I want to re-emphasize, if you want to be simpler, it's fine. There is nothing forcing you to set up all 3 trains like a full plant would be. You could have just plugged all this volume into one aerobic. Name. So if you make a mistake in the naming, don't worry. Internally, everything has a unique ID, this number ID, but you just rename it up. You got this. Now, let's have this diffuse aeration 0.6, and we said this is 22% efficiency, and let's say the set point over here, we want to maintain this end of the tank at 3 milligrams per liter. The first part was 2.5, now this is 3. Okay. Now, the next thing we will do is we need a nitrate recycle, and we need a secondary clarifier. Okay, let me first throw in the secondary clarifier. Let me leave some space here to put in a flow splitter for the nitrate recycle. So let's go in here and look for how I put in the nitrate recycle. Again, all of this is in chapter 2 of user manual part 1, A or B. So here's a nitrate recycle. So I went into the flow splitter, the green one is the nitrate recycle. Now let's say, okay, one thing about convention is that the main flow is going to flow through this. What is pumped out or what is split out is going to come out from this bottom of the tube. Let's say I want to flip it so that I can put this thing properly on my GUI. Let's say I use flip horizontal and that turns it around. This nitrate recycle is going to go in here and come back in here. So I need to go find a combiner to combine the flow, and I will combine it over here. And I will also flip this, and I will connect this to this. Okay. Now, so the primary effluent is going to come out from here and is going to go somewhere. But there's also a RAS, and now I'm running out of space, so I can move these things. There are different ways to move it. You can move it using the move right button, which if you click on this and if I click on this and I press move right, it will move very gradually, or I can just drag it and place it. So I'm moving these a little bit so that I can connect and have another place to bring in the return slot. Now, this return sludge, which is here, will go through a waste sludge stream and then come back here. So, do not forget to put in a waste sludge. So, let's say the waste sludge is from the return sludge line. Now, this is pointing the wrong way, so I'm going to do a flip vertical so that it points this way. So, here's my underflow. Here's going to be the waste sludge, and then the return sludge is going to come from here and join. I need another combiner because otherwise I can't bring in the primary class. So let's go back here and find another flow combiner and try to squeeze it in here. So I have some space issues. I'll just move things a little bit. And what I'm going to do is I can keep this here or sorry. And let's say this primary effluent is going to, first let me join this. This is connecting up here. So that is this. This is going to connect here. And this primary effluent is going to come and connect here. Now, here's my waste sludge. This sludge needs to go somewhere. There needs to be an endpoint or a dewatering unit. We won't cover the dewatering today. We'll cover it tomorrow. So for now, I'll just use the sludge icon and I'll put And the effluent from the plant is going to go from here to here. Now let's go back to the nitrate recycle. Let's call this nitrate recycle pumping system or nitrate recycle system. Now your nitrate recycle pumps may be sitting inside the tank, which is fine. In a more detailed class, I'll tell you how the hydraulic configuration is replicated. Within the nitrate recycle, if you look at the child asset, there is a flow controller. So the nitrate recycle can be set up in terms of different means. Okay, anytime you put in a flow splitter, you can choose either a percentage flow, that means a percentage of the flow that is coming in is going to go back here, or you can specify a particular liquid flow. For now, for this one, we'll use liquid flow. Tomorrow, when we set up dewatering, we'll use percentage flow. And let's say the nitrate recycle for this plant, it's flowing at 10,000 meter cube per day, so we'll put the nitrate recycle at 2 cube per 1,000 meter cube per day. So this is your nitrate recycle flow control. Now, when we go into equipment, we could set up the individual pumps under the nitrate recycle and turn pumps on and off. But today, for lack of time, I won't touch on the equipment. I'll just keep it simple like this. Now you get into the clarifier. Let's say this plant has 3 secondary clarifiers. So now, in the clarifier, for now we could turn the model off, but the model works in the sludge blanket layer, we'll keep it on. The TSS removal, we discussed a little bit under primary clarifiers. Let's say the clarifiers are removing about 99.7% TSS. What you do is you run the model and you look at your effluent against your real plant and you can change it. Let's say these clarifiers are 4.5 meters. Okay. And you are going to have multiple clarifiers, so we will set that up. Now, let's look at the child assets under the clarifier. There is the underflow. Okay, so this is the underflow coming out of the bottom of the clarifier. And for this plant receiving 10,000 meter cube per day, let's say the average for now, we just plug in the average is 60% around 6,000 meter cube per day. Now you have the clarifier tank. So let me call it secondary clarifier tank here. Now, we said we will install 3 clarifiers here. So I'll just go in and add the 3. If you're again doing a quick and dirty design, you might add the clarifier is not your responsibility. You may say, well, I'll just put in one big fat clarifier, a white care or 3. I'm not trying to replicate the clarifier part of the system. That's fine. And I'm putting in a dimension of 500. So let me just check I got these right. 25, 25. Okay. Now, let's say here too, I'm going to turn number 3 off. That's fine. Turn number 3 off. The other 2 are off. Now, one thing that is still missing is how much sludge I'm wasting. Now, you can have a pump sludge wasting. You can have just a flow split sludge wasting. This flow splitter also, I'll use liquid, and I'll say, okay, I am going to waste 200 meter cube per day of sludge. Okay. Now, I will call this divider over here. If you look, this is highlighted. I'll call it west. So there's his name. Was this name? Yes, this was also named. So if you look on this, we are trying to name everything here. And if you look through the color, you can open it up the hierarchy. You will see things have been named on the primary treatment, on the secondary treatment, all of this. And then you can open up the hierarchy further. So this is, okay, one important thing we forgot on the secondary clarifier is the SVR. So one of the things we do ask for when we run it is your SVR. So if you have data from your plant and the SVR is around 100, enter 100. If you want to be conservative, you can enter 100. So now we have set this part of the point up. Then you get into whether you want to make your model runs a little bit more sophisticated or a little less sophisticated. One of the first things you need to know, and when you go through chapter 2, you'll see you have the option of running steady state and dynamic. You obviously will run steady state first, and we won't cover dynamic today, but we can cover it in a subsequent class for tomorrow. You have solve or optimize. We're not setting up an optimizer right now, we just solve it. You have online and offline mode. It is running offline. Online is you're bringing data in continuously from SCADA. Now within the model, again, this is covered in chapter 2, but I will very briefly touch upon what all is there. But you do need to look at chapter 2, and you do need to look later on in subsections of 1 and 2. You can specify which soluble components, like this is the fermentable COD, this is the fermented, this is the unfermentable, etc., which components you want to run. For example, methanol, methanol, we are not feeding methanol, so you can turn it off. There's no need to burden the model with that. Similarly, we are not adding iron or aluminum, so we have turned those off. In particular, is the corresponding ones. Like if you want to run fermenters, you should turn that on. But methanogens, well, we are not running a digester, anaerobic digester, so that is off. Methanotropes, we're not feeding methanol, so that is off. Anamox, unless you're running a special anamox bioreactor, we ask you to keep it off. And same thing with ferric phosphate, ferric hydroxide, so it doesn't get off. So that's under model component. Then when you look at processes, several things are turned off as a default, but you could turn it on. If you want to run fermentation, turn the fermentation reactions on. If you have digesters, turn OAM on, etc. We are running the nitrifiers, we are not running anamox, we are not running the precipitation reaction. So what this does is it helps you make your model faster. Then you should go through and look up the SGM components. You don't have to tweak things that much over here, but if you look, there are ordinary heterotrophs, fermenters, methanogens in the digester, polyphosphate accumulating bacteria, the methanotrophs, which use the methanol or part of the methanol, the ammonia oxidizers, nitrite oxidizers, anamox, then you have hydrolysis coefficients, stoichiometry, and conversion factors. Within each of the bacteria, you have some general coefficients, then some coefficients for the under aerobic conditions like KO2 and the growth rate under aerobic conditions. You have under anoxic conditions, and you have under anaerobic. Now, again, go to chapter 2 and look up what you may want to modify. The only things you may want to modify at this stage when you're learning is this decay rate, especially if you operate at lower DOs. 0.15 is probably on the high side. It's probably more like 0.12 on the aerobic. Probably a little lower than 0.10 under anoxic. It's more like 0.08. So you may want to modify that. Then when you go into AOB and you look up general, your KO2 in real life plants may be a little less than this, but this is a conservative value. Your aerobic growth rate, this may be pretty close, but your K ammonia is probably also less than 1, more like 0.75. That's what we find in real life plants. So you may make a few adjustments like that. Hydrolysis, general, we can leave these alone for now, but under stoichiometry, we will make some corrections later on. One of them is production of fermentable COD and hydrolysis. Not that it will affect your simple model today, but we will change that to 0.8 or 0.95, something like that. And then there are a few others we may change. But I think what is more important for you to know is the fact that you can use something called local models versus global models, which is an advanced term. But if I were using an anaerobic digester, I would not use the same model which is applying to the aerobic bioreactors and the secondary plasmas in the anaerobic digester. I can change my version. And then you go in here and you change it to local and you specify that. So for now, we will stick with the global one. So that covers that one. Now, as far as running it, you go in here under options and you look through the user manual, there are several ways for you to improve your run, especially if you are having some convergence down. But first, we will just run calculate flows only. Okay. We want to see if our hydraulic network is connected properly. And we will start from the initial guess. And there are some, these are my initial guess of bacteria in the system, and I can refine these. In fact, you can go to a more detailed view of the initial guess if you press on this, and you can even specify how much ferric phosphate, etc. you have. But right now, we'll stay with the default values. So what I've done, again, going back here under general is I'm going to first calculate flows. So if I press calculate flows only and I press the start button, it says the network is fine. It has worked through it. Now, the next step is to run the actual model. So to do that, you will remove calculate flows only, and now you're going to run the matrix of equation. Now, one of the things you may have is some convergence issues in some instances if you don't have enough recycling. Now, there are ways to get over that. Well, this one didn't have any problems. But if you have convergence issues because you don't have enough internal recycle, that's because you're not replicating the mixing and the roll pattern in your system. Then what you do is you can go into this, in any bioreactor, you can go into the dampening flow, which is the internal mixing. And you can specify a value of internal mixing, it may be 2 to 5 times your influent flow or sometimes even much larger. But let's say we entered 20,000 meter cube. Not that this point needs it, I'm just showing it to you. 20,000 meter cube for the internal mixing created by this mixer within here. And in the aerobic zone, you can have aerobic roll back. That is only if you're having some issues with convergence. It's discussed in your user manual. Since I've run it, I'll be able to see the concentrations in any of these flow streams. So for example, I can click on the primary effluent and I'll see, okay, primary effluent, TSS, TKN, etc. Okay. So I go over here and I look at my functional effluent and I say, okay, I have 0.65 ammonia, 6.5 or so nitrate, 1.5 TKN, etc. And I've finished running the model once. Now, if you look at these flow streams have the default names. But let's say I want to name this secondary effluent. I'll just go in here and I'll call this secondary effluent. So this is called secondary effluent. If I want to name this guy primary effluent, I click on this one, it will name primary effluent. And so on. If I click on this one, this is raw effluent. So it is good practice if you want to reuse the model and also go rename this. Once you rename it and you save it, you're done. Okay. Now let me just go through 2 more things here. One is I haven't shown you how to save your model. So you go here, File, Save As. And when you go to Save As, you type in your name. So today was class February 6th. Okay. And I press save. And when you press the save button and you go into the folder, you will now see 2 files created with this name, class February 6th IVO and IVO1. This one here contains the dimensions of your reactors. This one will contain the data from the run. If you run dynamic simulation, this file will become much larger. Now, if I want to send a file to you, I can decide to send both, or I can decide to send only this, and then when the other person runs it, it'll generate this other file. So the big data file with dynamic simulation data is separated from this so that it's easier to send files back and forth. But you will always see an IVO and an IVO1 file created. When you go to upload the file, you will only see the IVO name because you really don't need to see IVO1. If IVO1 is missing, you won't just upload that part. You'll just upload the IVO, which will have the dimensions of your reactor. So you got the save part. Now Now, the two other things that I want to touch on today is setting up a calculator, if you have that. Now, but before we go there, let's say you want to set up your some other things. You want to set up your liquid temperature. Your liquid temperature, let's say you want to run it at 15 Celsius. You change this temperature here to 15 Celsius. You can even connect it to a time series data. And I want to rerun it. I will press the start button and I rerun. Now, when I'm rerunning it, it rerun all the way from initial guess. So it took a little bit longer. And my ammonia right now has gone up to 1.85. It's greater than 1 milligram per liter. But I could decide that I do not want to rerun from initial guess every time. So I go in here and I uncheck initial guess. And when I press rerun, start, it finishes immediately. Now let me check the mix liquor on the way to the clarifier. The mix liquor is 1985. So it's pretty low for the tanks that are operating. I could decide, okay, I want to waste less. I want to waste 100 meter cube per day instead of 200 meter cube per day at 15 Celsius. And I want to rerun it with 100, it'll rerun and it'll converge. So this has finished running. And if I look at the effluent, right now the ammonia is down to back from 1.85 to 0.5. I can go ahead and save this and just overwrite the other file. Now, if you want to set up an MCRD calculator, you can set it up at any point in the hierarchy, but we'll set it up under plant. Under plant, again, it's in your user manual. Go to MCRD and say, okay, I want to set up, you can set up 2, 3, 4 MCRD calculators. You can set up one with the clarifier, one without the clarifier, one for your anaerobic digester if you have one. So let's say this is the MCRD calculator, MCRD 1 with clarifier, okay, with secondary clarifier. Now in an MCRD calculator, you have to go in here and you have to select which ones belong to this MCRD. So an arctic one belongs, aerobic one belongs, and the sludge layer and the secondary clarifier. Now you go to flow streams and you have to say what is removing your sludge from your system. Well, one of them is secondary effluent, but now I can't figure out which one is WAS because I have not named the WAS flow stream. So I go in here, I click on this, and I say, okay, this, when I click on this, it says it is this one. So I go in here and I call this waste activated sludge. Okay. Now I go back to my MCRD calculator. And I select, okay, there are two flow streams which are taking sludge out, secondary effluent and WAS. So I have clicked on these. And now if I rerun it under output, it will give me the MCRD. So go in here, go to output. It's giving me a 21-day MCRD. So my system with the clarifier is running at 21-day MCRD. Now, you could go into, if you're in steady state, or in dynamic simulation, you can go into the results tab and you can look at results and graphs over there too. This is more useful in steady state. But go to the flow streams, let's say go to your secondary effluent, and you will get your TSS, your COD, etc. over here. So you can see the results right over there. And if I want to shut off, it's got buried under some other screen, I'll just close it.